Hello viewers, welcome to this next lecture on the NPTEL MOOC course on mathematical portfolio theory. You would recall that in the last class we started off on a new topic, namely looking at risk measures beyond the Markowitz setup of variance or equivalently standard deviation, and we identified two important risk measures, namely value at risk and conditional value at risk. And in the previous class, as a prelude to the discussion on value at risk and conditional value at risk, we introduced the concept of what is quantiles in terms of the cumulative distribution function, and we looked at some of the examples. So, in today's class we will be focused on starting our topic discussion on the topic of value at risk or VAR, and then we will look at some of the properties of VAR, and we will conclude with looking at what is going to be the VAR in case of a risky asset, namely a stock which follows the geometric Brownian motion. So, accordingly we start this lecture. And this will be basically a part of the broader discussion on measuring downside risk, and you have already seen some of the downside risks when you are talking about the non-mean variance framework. And for the sake of brevity, we work on a single step financial market model in which we invest at time t is equal to 0 and terminate our investment at time t is equal to capital T. So, that means that the investment horizon is going to be some time t equal to 0 when the investment is initiated, and at time t equal to capital T when the investment is terminated. So, we denote by x the discounted value of the position at time capital T. So, basically if you look at the value of your position at time t and you take the discounting of that particular random variable, that is the discounted value of the random variable at time t given by the value of the asset, that will be denoted by the new random variable x, and for subsequent discussion we will essentially, when you talk about a random variable x, we will mainly be focused on this particular random variable. Alright, so let us start off with the definition of value at risk. So, for some alpha which lies strictly between 0 and 1, we define the value at risk, which is abbreviated as VAR, as I mentioned yesterday, with the R in capital, of x at confidence level 1 minus alpha as follows. So, this var of x at confidence level alpha is indicated by a superscript of alpha. So, actually the confidence level is 1 minus alpha, and I indicate this with a superscript of alpha. This is defined as nothing but minus the upper quantile of x, and this is minus, and what was the definition of upper quantile? This was infimum of x such that alpha less than fx of x. So, how does this look graphically? So, we take the random variable x on the x axis, and on the y axis we of course have fx of x. Then the cumulative distribution is something that obviously is going to look like this, and eventually of course it as your as your x increases, this value approaches 1. Now what we do is that we fix some value of alpha out here, which obviously lies strictly between 0 and 1, and we look at this horizontal line corresponding to alpha, and then we identify the corresponding value on the x axis. So now you observe that, see, this line is the line for alpha. So the region that is satisfies the condition that alpha is strictly less than f(x) of x, that region is going to be nothing but, since your alpha is less than, so it is basically this region that you have here, this region will be alpha is greater than f(x) of x, because alpha lies above the curve here, and this region is the region where you have alpha is strictly less than f(x) of x. So accordingly, when I am going to calculate var, that is equivalently I have to calculate the minus infimum of all those x's for which alpha less than f(x) of x. So I consider this region where alpha less than f(x) of x, and consider all the x's which are basically this part. So it is essentially all the x's from this part onwards, and I look at the smallest value of x, right, and the smallest value of x, and in this region of alpha being strictly less than f(x) of x, that smallest value of x will be given by this. And what is this? This by definition is q alpha of x, and from here you see that q alpha of x is nothing but minus var of x. So essentially what you need to do is that we look at that cumulative distribution of x, and then we identify what is this x for what is q alpha of x, and that is the same as minus var alpha of x. Okay, so now let us observe. Now let us observe this very carefully, that since what was x? You recall that your x was nothing but the discounted value of the position at time t. So obviously x denotes the gain from an investment, right. So x will be something like e raised to minus RT ST minus S0. So you look at your original investment S0, and e raised to minus RT ST is the present value of your final wealth level. So the difference between them is obviously going to be the gain. So accordingly x is here, it should be interpreted as the gain from a particular investment, and since x is the gain, so therefore minus x denotes the loss. So once with this observation that minus x denotes the loss, we can now express var in terms of loss as follows. And what is this going to be? So just what is the definition of var? Var alpha of x is equal to minus q alpha of x, and this you would recall from the result done in case of quantile. This is going to be nothing but q of 1 minus alpha of minus x. So recall that we had already done this result. So it is one of the results that we had done in yesterday's class, or rather the previous class, and this is and what is this by definition? So var alpha of x equal to minus of upper quantile of x by definition of var, and this from the result we say that this is q of 1 minus alpha of minus x, and this is now the lower quantile. So, this by definition is the smallest value of x such that this 1 minus alpha is less than or equal to the cumulative distribution function or probability of the random variable minus x being less than or equal to little x. So, this is an alternative form of writing what is going to be my var x of alpha in terms of the loss variable. And this can be written as it is the smallest value of x such that probability of x less than minus x is less than or equal to alpha, right. So, how do I obtain this? So, basically I have 1 minus alpha is less than or equal to probability of minus x less than or equal to x. This implies that probability of minus x, so this will imply that 1 minus probability of minus x being less than or equal to x is less than or equal to alpha, and remember that 1 minus probability of minus x less than or equal to x is nothing but probability that minus x being greater than x is less than or equal to alpha, and this implies that this is probability of x being strictly less than minus x less than or equal to alpha. All right. So, basically I have taken this expression and got the equivalent expression here, which I have substituted out here. Okay, now let us look at this new form of var in this as a part of this expression and see what it means. So, we can state that this means that the probability of the loss exceeding var of x is no greater than alpha, or in other words, at the confidence level (1 minus alpha), our loss is no worse than var alpha of x. So, var alpha of x is the number which says that at a confidence level of 1 minus alpha. So, for example, if your alpha is 0.05, so 1 minus alpha is 0.95. So, suppose that we have alpha is equal to 0.05, then 1 minus alpha is equal to 0.95 or 95%. So, in that case we say that in 95% cases the loss is no more than var of 0.05 of x. Okay, now let us just briefly enumerate some properties of var. So, let us start off with x and y be two random variables. So, the following properties hold. First of all, x is greater than or equal to y implies that var alpha of x is less than or equal to var alpha of y. Secondly, for any a belonging to R, that is any real number a, var alpha of x plus a is equal to var alpha of x minus a. And the third point is that for any non-negative a, var alpha of a x is going to be nothing but a var alpha of x. And you see that these are corresponding to the first three properties that we had proved in the previous class, and of course, the fourth property already we have made use of here. So, let us just give a quick proof for each of those. So, the proof goes as follows. So, if your x greater than or equal to y, so for the first one, what do we have? We have x greater than or equal to y. So, then var alpha of x is going to be by definition minus of upper quantile of x. Now, when your x is greater than or equal to y, this relation results in minus q alpha of x into q alpha of y, and minus q alpha of y, that is the minus of upper quantile of y, by definition is var alpha of y. For the second result, what we do is again we just make use of the definition. So, what is var alpha of x? Var alpha of x, so var alpha of x plus a by definition is minus q alpha of x plus a, that is the upper quantile of x plus a, and the q alpha of x plus a, we have already seen that this is upper quantile or q alpha of x plus a, and this can be written as minus q alpha of x minus a, and minus upper quantile or minus q alpha of x, this by definition is var of x minus a. So, we have proved these two results, and for the last result we have var alpha of a x. Remember, a is greater than or equal to 0. This is what is going to be. This is going to be minus of q alpha of a x by definition, that is minus of upper quantile of a x, and this can be written as upper quantile of a x by the result for quantiles. This is a into q alpha of x, and this can be written as a into minus q alpha of x, and this by definition is that a var alpha of x. Okay, so far what we have done is we looked at what is the definition of var in terms of the upper quantile, and then we were able to translate this to an equivalent definition of var, and an interpretation of this is that var at a certain level alpha indicates that we can say that with 1 minus alpha percentage or 1 minus alpha likelihood that the var will that the losses will not be exceeded, will not exceed this amount of var. So, when I say that my alpha is equal to maybe 10% and the corresponding var is some v, then what you are really saying is that there are 90% chances are that the losses are not going to exceed this amount of v, and 10% chances are that the losses are going to exceed this amount of v. So, what it does is that at a certain level of confidence, it essentially gives a threshold which indicates that the likelihood that at this particular likelihood level gives the chances of chances of the losses exceeding that value at that particular value of alpha. So, what it essentially does is that it looks at the distribution of the returns and essentially bifurcates that into two parts, with the cutoff being at var, and then you essentially identify that the chances of losses being above or below that particular level, and that is linked with what is going to be the corresponding confidence level. So, the cutoff will essentially depend on what is the confidence level. So, if you choose a different value of alpha, then obviously you are going to get a different value of var. So, every definition of var obviously, or any result on var must be accompanied by the caveat that you have to specify what is going to be your level of alpha. So, the next thing we do is we look at the example for computing var, and we will look at a few of those examples to illustrate how the computation is done. So, for this purpose, what we shall do is that we shall assume that at time t is equal to 0, we invest an amount of V 0 to receive an amount of V of capital T at time t is equal to capital T, right. So, this means that you have these two timelines 0 to capital T, and you invest V 0 and you end up receiving an amount of V of capital T. Further, we use the random variable x to denote the discounted gain at time t is equal to capital T. So, that is x is going to be e raised to minus r into t into v of t minus v 0, where r is the risk free rate with continuous compounding. All right. So, let us start off with the first example, and this is going to be the simplest possible example, and we assume that we invest an amount V 0 at risk free rate R. So, in this case, what is V of t going to be? It is going to be the investment of V 0 growing by a factor of e raised to r into capital T. So, therefore, what is x going to be? X is going to be e raised to minus r t V of t minus V 0. So, actually this is just the definition of x that we have given earlier. And what is this distribution going to be? See, observe carefully that this x essentially is going to be equal to 0. All right. So, this means that x is basically going to just take one value, and that is 0. So, what is going to be the corresponding distribution function? So, here when your x is less than 0, then obviously the probability of that happening is going to be equal to 0, and your x being greater than or equal to 0 is going to be 1, because you know for certainty that x will take the value of 0. So, this is going to be your cumulative distribution function f x of x. Okay, now that you have the cumulative distribution function, obviously then you can calculate your quantile. So, for any alpha belonging to 0 1, what is going to be your quantile, upper quantile? Your q alpha of x is going to be equal to 0. All right. So, because you need to consider the situation where your alpha is less than f x of x, and that the smallest value for that is going to be 0. So, your upper quantile is 0. So, from the distribution function you have got the upper quantile, and immediately the value at risk turns out to be equal to minus the upper quantile of x, and that is going to be equal to 0. And now you see that you observe that intuitively this is what you are going to expect, because it is like an investment in a bond, that you invest an amount of V 0, and then the discounted gain is simply going to be equal to 0, that is e raised to minus t into V of capital T minus V 0 is going to be equal to 0. And the reason why the value at risk is going to be 0 is that because it is a bond, and of course, assuming that you are holding on to the bond up to time capital T, and that is the same as the maturity of the bond, obviously you are not going to lose any amount of money. And when you are not going to lose any amount of money, that means that you are not going to suffer any losses, and so that means that the value at risk, that is the amount of money that you are likely to lose, naturally is going to be equal to 0. So, this is the simplest case of estimating what is the value at risk. Now, let us move on to another example. As this time, of course, we will have to take into consideration what is a risky asset. So, we start off with the second example, and in this case, suppose that we have an x. So, that means your x is say it can take two values. So, suppose that x equal to minus 20, that means your return is discounted gain is going to be minus 20 with probability 0.025, it is going to be minus 10, with probability 0.025 and probability that x is greater than 0 is going to be 0.95. So, either x takes the value -20 or -10 or simply positive values with the respective probabilities being 0.025 each for the first two cases and 0.95 for all the positive gains. Okay, then what is going to be my f(x) of x? So, you see if your x is less than -20, strictly less than -20, then the probability is going to be 0. So, f(x) of x is going to be 0. When your x is lies in the closed interval -20, that means this value all the way to -10, but excluding 10, then the corresponding probability will be 0.25 and the cumulative probability is also going to be 0.025. Likewise, when x is from -10 to 0, right, then you will essentially get again. So, now I have to include this probability of 0.025. So, the cumulative probability will be 0.05 and when x belongs to 0 to infinity we will get. So, this I will make it as greater than or equal to 0. So, this turns out to be equal to 1 because I have to add this probability of 0.95. So, this is going to be the cumulative distribution for this random variable x. Now, we consider three values of alpha. So, suppose we consider alpha equal to 0.05, 0.025 and 0.005. Then what is going to be the corresponding var alpha of x? So, in the first case var alpha of x is going to be minus q raised to 0.05 into x, and from here we see that this value is going to be equal to 0. In the second case, it is going to be minus q of 0.025 of x, and so from this two we get that this is going to be minus of minus 10, which is 10. And finally, we get the last var to be minus q of 0.005 of x, and this is in this particular range. So, this is going to be minus of minus 20 and this is going to be equal to 20. So, why did I do this example? The purpose of this example is that this example shows something that I have already mentioned, that the var alpha of x is sensitive to the value of alpha. So, for different values of alpha, you are actually getting different values of var for the same distribution here. Let us now consider a third example. So, we consider two independent investments with discounted gains being denoted by x1 and x2. And here I specify that in both the cases xi is equal to 0 with probability of p, that means the discounted gain is 0 with probability p, and the discounted gain is 1 with probability of 1 minus p. So, this is just a hypothetical example, and of course, this holds true for I equal to 1 and 2. So, this example to relate it to the real life, so we can think of this as corporate bonds with identical price and maturity of two independent companies that each have a probability of default with 0 recovery being equal to P. So, these are basically some corporate bonds, and this can so this have a maturity value of say 1, but since this is a corporate bond, so since this is a corporate bond, so it is risky. So, only one of the two things can happen, either the company is able to pay back its promised amount of 1, or it defaults and there is no chance of recovery, in which case you receive an amount of 0. So, accordingly this means that and when you receive an amount of 0, that is the state of default, and when you receive an amount of 1, or that is the discounted gain 1, this is a case of no default. And we assume that since the probability of default is P, so that is one reason why we say that xi takes the value of 0 with probability P, and likewise for no default the probability is going to be 1 minus P. So, now suppose that your P is strictly less than alpha. So, you would have chosen some alpha and your P is strictly less than alpha, then it follows that var of x1 is the same as var of x2, which is equal to minus 1. Okay. So, this means that if your P is less than alpha, then your value at risk for x1 or value of risk of x2, these are individually, both of them are equal to minus 1. So, that means an exclusive investment in the first bond or an exclusive investment in the second bond results in the value at risk being equal to minus 1 if P is less than alpha. Alright. So, we consider an alternative strategy and say that if instead we buy half unit each of the two bonds, then our gain will be the random variable half of x1 plus half of x2. Now, what are the values that this random variable can take? So, what can happen is that you could have, so if I take x1 and x2, if, so either x1 defaults and x2 defaults, that is one possibility. If or x1 may default, but x2 does not default, or you can have that x1 does not default and x2 defaults, and you can have that neither of them default. So, when both of them default, the probability is going, and you remember that I had said that these are two independent companies. So, this means that the probability of both the defaults, this probability is going to be simply p square. The probability of a single default, say in this case as well as in this case, and one no default, these probabilities are going to be p into 1 minus p and p into 1 minus p, and the probability of no default in both the cases, this is going to be 1 minus p whole square. So, this means that this random variable half x1 plus half x2 either can take the value half of the sum of these two, which is 0, or it can take the value of half of 0 plus 1 or 1 plus 0. So, that is simply half, or it takes half of 1 plus half of 1, which is equal to 1. So, for this value of 0, the probability is p square. Now, for these two cases, we have the combined probability to be equal to twice p into 1 minus p, and the third case we have probability 1 minus p square. So, if we choose alpha to be in the interval say p plus p square plus twice p into 1 minus p. Suppose we choose this alpha. So, this means that obviously this means that alpha is greater than p, right. So, it is consistent with this condition. So, if I choose an alpha in this case from this interval, that will satisfy this condition, and then I choose the same alpha in the second case. So, then what happens? Then the f(x), f of half x1 plus half x2, that means the distribution function of this random variable, the cumulative distribution of that at when it takes the value half. So, this is going to be what? The cumulative distribution of this up to half is simply going to be this probability plus this probability, which is p square plus twice p into 1 minus p, which is greater than alpha. So, this means that my f(x) of x is greater than alpha, and hence what is going to be the smallest value for which this is greater than alpha. So, hence var of half x1 plus half x2 is going to be equal to half. So, you observe that hence the value at risk of half x1 plus half x2 is going to be greater than either of this. So, I can write that in the form of maximum of var of x1 and var of x2. Okay, so let us come to the main point in actually bringing this example into the picture, and this means that the risk of a diversified portfolio or a diversified position as measured by var. So, this is the var of the diversified portfolio, because you have invested in both the bonds, is greater than the risk as measured by var for an investment in a single bond. So, the immediate ramification for this is the following, that this runs counter to the principle that diversification would reduce risk and therefore illustrates a drawback in using var to measure risk. So, let me elucidate this in a little more detail. See, when you started looking at var, var gave a very nice improvement over using standard deviation, because as a measure of risk, because it looked at some sort of a worst case scenario in 95% of the time, or rather or equivalently say in the 5% of the time. So, when I say that we are looking at 95% var, so it basically means that we are 5% certain that the losses will not exceed, will exceed a certain amount, that is the var, and 95% chances are that you are safe and the losses will not exceed that amount. So, this might also, so this is certainly an improvement over using just the standard deviation as a measure of risk. However, we must also keep in mind that at the heart of portfolio theory, in the paradigm of the Markowitz framework, the key aspect towards achieving a portfolio optimization is diversification. And through this example, in which we consider two individual bonds and then a combination of those two bonds which are identical. So, that means that your initial investment is identical in case of the individual bond or a half and half investment in those bonds. and it turns out that in this case the value at risk that you have for alpha being greater than p, it turns out that as a result of diversification, the value at risk actually has increased as compared to a situation where you would have just invested in either of the individual bonds. So, this essentially is a single counter example, and there are many such counter examples that you can create, which says that the value at risk, while being a good alternative to using standard deviation or variance as a risk measure, suffers from these drawbacks that not in all situations can you achieve an improvement in terms of risk reduction just because you have carried out diversification. And it is this key weaknesses in case of value at risk that motivates the usage of the introduction and usage of the conditional value at risk that we are going to introduce in the next class. So, let us continue our discussion keeping in mind this shortcoming, but nevertheless keeping in mind the usefulness of VAR as compared to just the standard deviation. Let us now continue our discussion and elaborate a little more on this by looking at a couple of important results, one in the discrete case and one in the continuous time case. So, we first present this result 1. It says the following, that assume that x is a discrete random variable with probability x equal to xi, say, is equal to pi. So, suppose that I have this discrete random variable x, which takes the values, capital N number of values, which I denote by little x1 through little xn, and I denote the corresponding probability with as little p1 through pn. And here we say that, so obviously the summation of pi I is equal to 1 to n, this is going to be equal to 1, and we arrange them in an increasing order such that x1 less than x2 less than x3 all the way to xn. So, we have these random variables, and suppose that we arrange these random variables in increasing order, the reason for which will become very clear, and we identify the corresponding probabilities of the random variable taking any of these increasing values or these ordered values xi to be equal to pi. Then what is the value at risk? Then value at risk of x, this is going to be simply minus a x subscript k subscript alpha. And what is this x cross subscript k subscript alpha? So, where this k alpha is naturally going to be a natural number, because it is one of those 1 through n's, is the largest number such that the summation probability pi's I equal to 1 to k alpha minus 1, this summation is going to be less than or equal to alpha, and the reason for in this definition being introduced will be clear once we do the proof. So, let us start the proof for this. Now, since x has a discrete distribution, and your x1 is less than x2 all the way to less than xn, we can see that probability that x is less than or equal to xk, and since these are ordered, so obviously probability that random variable x is less than or equal to xk is going to be summation pi I is equal to 1 to k. Now, we shall also use the fact that minimum of all those k's such that alpha is less than summation pi I is equal to 1 to k. This will be simply the maximum of all those k's such that summation pi I is equal to 1 to k minus 1 is less than or equal to alpha. So, basically you can observe this very easily if you actually look at the ordered values of p 1 all the way to p of capital N, and you basically set the alpha to be some sort of a bifurcation criteria. So, here of course, alpha is pre-specified. So, accordingly you identify the two probabilities in between which this alpha lies. So, it is possible that alpha, so accordingly you will essentially have that the sum of the probabilities in one case will be less than or equal to alpha here, and sum of the probabilities in the other case is going to be greater than alpha. So, essentially this means that you look at the cumulative distribution of the probabilities, and then you essentially identify the point where alpha is going to lie, and so essentially alpha is going to lie between some case. At some point you are going to switch over alpha being less than a summation of all the probabilities to the situation where the alpha is going to be greater than or equal to sum of all the probabilities, and that switching point is the one and using that. So, essentially that means that in one case the minimum the value of k is where alpha is less than summation of pi, that is the same as the that is going to be the index for which the switching will happen, and that is going to be exactly the same as the maximum of that value of k, such that alpha is going to be greater than or equal to summation of all the pi's. So, once we have identified this fact, so therefore, we are now in a position to calculate the upper quantile, which then can of course be used to calculate what is the value at risk. So, the upper quantile by definition is the infimum of all those x such that alpha is less than probability of x less than or equal to x, and this is nothing but it is the smallest. So, what are these x values? These are x k. So, it is the smallest x k such that alpha is less than probability of x less than or equal to x little k, and this is minimum of x k such that alpha is less than summation p I is equal to 1 to k. So, this comes from the definition of this probability, and this minimum is not going to be nothing but maximum. So, making use of these results. So, these k's are obviously, this can be replaced by x k. So, this is going to be maximum of all those x k such that summation of pi, so this term here I equal to 1 to k minus 1 is less than or equal to alpha. And what is this? This is precisely what we had defined to be our k alpha. So, this is going to be nothing but x of k alpha as defined in the statement of the result. So, we are done. So, therefore, since the upper quantile is x k alpha, so therefore, the value at risk is negative of upper quantile, and this is minus x k alpha. All right. So, now let us make a note that, so let us now move to the continuous time setting. So, if x is a standard normal random variate, that is n of x, the cumulative distribution of this is 1 over square root of 2 pi into integral minus infinity to x e raised to minus z square over 2 into dz. So, then your var alpha of x, if x is a standard normal random variate, this is simply going to be minus n inverse of alpha, and the reason is that we make use of the result that the upper quantile q alpha of x is simply going to be minus n inverse of alpha is equal to minus f x inverse of alpha. So, you will recall one of the results, and since the cumulative distribution is the cumulative normal distribution, so that is why I get minus n inverse of alpha, and this happened if f x is continuous and strictly increasing, which is the case in case of the normal distribution. So, this means that if I take x to be a standard normal random variate, and you recall this result for the upper quantile being given by this. So, if your x is a standard normal random variate, so then the x is your n01. So, essentially then this will become simply minus n inverse of alpha. So, I found out what is the var in case the random variable x is normally distributed, and that is going to be minus n inverse of the pre-specified value of alpha. And now we are now in a position to do our second result, and we have to recall the geometric Brownian motion model. So, suppose that the price of an asset today is S0, and suppose so this asset is a stock, and suppose that the price of the stock at time capital T is S of capital T. Now, you will recall that S of capital T, this is given by S naught S of 0 into some e raised to m plus sigma z, with z following n01 distribution. So, we recall that one of the forms which this was given was S0 is equal to St equal to S0 into e raised to mu minus half sigma square into T plus sigma of W of T. So, this is another way of writing where we take this term to be m, and sigma of Wt is going to be simply sigma of z. Remember, Wt is n01, n0t, right. So, this actually should be written as this is sigma of Wt, and this can be rewritten as sigma into square root of t into some n01 distribution. Okay. So, what is going to be the x? So, accordingly the x, which is the discounted gain, is e raised to minus RT into ST minus S0. And also from here you know that q alpha of z, because z is n01. So, from here we get q alpha of z is simply going to be equal to n inverse of alpha. So, just a slight correction here, this is actually plus. So, that is how I got the, so the var was minus of this. So, please make this correction, this is actually plus of n inverse of alpha. So, I just reproduce this result here. So, we have three things now. We have S of t, a formula for that using geometric Brownian motion. Accordingly, we calculate the discounted gain, and since we have a z sitting here which you will need. So, accordingly we consider we just note that q alpha of z is equal to n inverse of alpha. So, from this result. Okay. So, now observe that x is equal to f of z. So, I mean by x I mean this x, where this function f say zeta is nothing but, so e raised to minus RT, and what is ST? ST is S0 into e raised to m plus sigma. So, let me actually write this in detail. So, this is going to be e raised to minus RT. So, we have e raised to minus RT, ST minus S0. This is e raised to minus RT into S0 into e raised to m plus sigma z. So, therefore, I can define f of zeta, which is this is going to be e raised to minus RT S0 e raised to, so there is a minus S0 e raised to m plus sigma zeta minus S0. So, if I put zeta is equal to z, then we get back or recover this relation. Okay, now you observe carefully. Now, this f of zeta is an increasing function, right. So, therefore, what is we get? We get var alpha of x. What is this going to be? This is by definition minus q alpha of x, the minus of upper quantile of x. What is x? X is f of z. So, this is minus q alpha f of z, but f is an increasing function. So, I can interchange this q the quantile and f. So, this becomes minus f of q alpha of z. What is q alpha of z? Q alpha of z is n inverse minus alpha. So, n minus f inverse alpha. This is q alpha of z is n inverse of alpha. So, just a correction. So, this is minus f of n inverse of alpha, and now we have to evaluate the function for zeta equal to n inverse of alpha. So, this becomes minus of e raised to minus r t S0 e raised to m plus sigma n inverse of alpha minus S0. So, I have just replaced this zeta with n inverse of alpha, and this can be written as S0. So, I take the common factor of S0 out, and this becomes 1 minus e raised to, so the S0 is out and we combine m and RT. So, this becomes e raised to m minus RT plus we have this sigma n inverse of alpha. So, we just have a last brief result which says that let f from R to R, that is a real valued function, be a non-decreasing right continuous function, then var alpha of f of x is going to be minus f of q alpha of x. And the proof for this is extremely straightforward. What is going to be, start with the left hand side. So, var of f x is going to be by definition minus q alpha of f x, and we just interchange the f and q. So, this becomes minus f of q alpha of x. Alright, so this brings us to the end of this discussion on value at risk. So, just to do a recap, we picked up from the results that we had done last time on the quantiles, and we now introduce the definition of value at risk of x to be negative of the quantile of x, and we gave an interpretation of the var in terms of looking at the loss and the percentage level with which you can predict this loss. We looked at 3 different examples. The first was to recognize that the value at risk in case of a bond, since it is a risk free asset, is going to be 0. And then we looked at another example in case of the value at risk in case of a risky asset. And finally, we looked at a very critical example of value at risk, which shows that diversification does not necessarily lead to reduction in the value at risk. And we identified that this observation of the failure of diversification in achieving a lower measure of risk as given by the value of value at risk is something that is going to be used as a motivating reason for moving on to what is the conditional value at risk. And then we looked at a few results, primarily the result pertaining to determining the value at risk in case of a random variable taking the discrete values and provided they are ordered in increasing fashion. And then we looked at what is going to be the value at risk in case of a random variable following a standard normal random variate, which then was used to calculate the value at risk of a investment in a stock where the behavior of the stock is modeled in the continuous time framework using the geometric Brownian motion. So, this brings us to an end to the discussion on value at risk, and in the next class we will conclude this topic with a discussion on what is the conditional value at risk. Thank you for watching.